So, in box 2, which you play with, yeah? So, the thing is this. This is one of the great gotcha problems of integration by parts. And students once in a while have trouble with this because they have selective vision. You guys are way past this, but it's very common when you have a Calc 1 student that they just write an integral like that. Now, obviously, what's wrong? There's no differential. Now, you might think, well, who cares? What's the difference? Well, there's a big difference because if I put a dy there, then the antiderivative is y arctangent of x plus c. And if I put a z there, then it's z arctangent of x plus c. But if it's dx, well, then it's integration by parts and it's inverse. Okay? So does that thing matter? Yeah, a lot. Okay, because that tells you the variable of integration, and that tells you all. That's especially important in multivariate, which you're going to, Calc 3. You will see double integrals. Arctangent of x dx dy. Well, you integrate once with respect to x and the next with respect to y. My point, though, is that it matters a lot. Okay? Now, then, once we've decided that dx matters, then it also helps to know or remember. I'm pretty sure that's supposed to be. All right. Isn't that a thing? Yeah. Okay. Okay. That's so little. All right. Then, this is a thing, and you need to see it, not just something that tells you what to integrate with respect to, but it is also a term. And so this, though it doesn't feel like ultraviolet voodoo because it's not a product, it is a product because dx is a factor. And so you should consider this here as a possibility. The ultraviolet voodoo, the ultraviolet voodoo pattern goes a little like that. So what's U? Arctangent, good choice. Arctangent of x. By the way, I used arctangent there, but the inverse tangent notation is used all the time interchangeably. No big deal there. So don't sweat that. What about then dv? dv must be dx. Cool. If u is arctangent, then du is 1 plus x squared dx, and v is the antiderivative of dx, which is x. All right. Using the pattern, remember it's negative. A lot of people will remember it as positive, so remember subtraction. Okay, so uv is x, arctangent of x, and then we get an integral that's a little complicated. X over 1 plus x squared dx. That's a plus, not 6. Okay. Well then, what's the approach for that integral? What would you do? U sub. Actually, W sub, because U has already been used, right? So maybe W sub. Now, this is where I kind of get to know you. When you say U sub, on a problem like that, would you actually U sub it, or would you, what I think of as mental U sub it? Do you have any idea what I mean by mental U sub it? All right, well, this is what, okay. This, I'm just throwing it out there as a possibility. This could, you guys are pretty experienced with U sub. So just mentally, what's your U? 1 plus x squared, right? So what's du? 2x dx. Now, in my mind, then, I would say, gosh, I would love for this to be a 2 there. Can I put a 2 there? Well, yeah, I can, as long as I balance with something I have. So then this, I would say, is, okay, now it's u over du over u, 1/2 natural log of sub back, boom, done. Okay, now, if that works for you, great, I'm cool with that. You will get there eventually, I promise you, because, I mean, that's going to be such a small part of a lot of big problems. But if that's not the case yet, and you feel like you would be safer going with W sub, let's do that. So if W is 1 plus x squared, then dW is 2x dx. If I isolate the x dx, then dW over 2, or 1/2 dW is x dx. And with substitution, this becomes something like x arctangent of x minus 1/2 du, dw rather, over w, the antiderivative of which is 1/2 natural log of the absolute value of e plus c, and then step back. You can do that in one step, and I'm fine with that. Arctangent of x. Would I need that absolute value given that it's x squared plus 1? Why not? Sorry, positive. What's a possible other form of the solution you might see in a multiple choice, given log rules? Natural log of the square root of x squared plus 1 is a possibility, right? Okay. Does that work for you? It's very much the same kind of problem as this classic problem. And I guarantee you, I'll slap that on a test, and I'm going to put choice A, 1 over x. And boom. People are going to go right on that all day. Now, is that the antiderivative of natural log? No, that's the derivative. So slow yourself down, slow your roll, as the kids say nowadays, and actually integrate by parts. And that is just like this guy. It feels like it's not integration by parts because it's so clean, but it is, because dx is a thing, right? Okay. This guy, did this go pretty well? That's more of a common integration by parts. What did you let u equal? 3x, and therefore dv is. Now, what about that? E to the 2x dx. When you integrate to get v, do you u sub that, or do you do that? Do you really u sub that? Do you do all this? Oh my God, really? Really? So much work. Can we just say, oh, that is 1/2 e to the 2x? Yeah, let's go there. Let's not show all that work. Come on. Let's be quick and lazy, shall we? Right on. Okay, so uv, it's not lazy, it's just working smarter. 3/2 e to the 2x minus 3/2 e to the 2x dx. This should be 3/2 x e to the 2x, yes? Okay, sorry, 3/2 x e to the 2x minus 3/2 e to the 2x dx. Let's integrate that. What's the antiderivative of that bad boy? Minus the 3/2 I can pull out front. What's the antiderivative of e to the 2x again? 1/2. So with that 3/2, it becomes 3/4. Right? That go okay? All right. Do you feel like integration by parts is pretty good? This actually has 3 different levels. If this is one level, there's also called circular integration by parts, which we'll do this year, and then tabular integration by parts. All those are skills to be learned soon, but not today. Let's go to set 70 on the back. Would you turn it over to set 70, find where number 10 is after set 70 starts, and I want to communicate the lesson from set 70, which is really, really straightforward. Set 70 is rules for limits. Now this is usually day 2 in a calculus class. It's supposed to be taught long, long ago. Why set 70 in our book? I don't know, but it's very basic. The only thing you have to worry about is what I need to see. The answer is no-brainer. This is an example here. They tell you in the book that the limit as x goes to 1 of a function is pi. The question is, given that fact, what's the limit as x goes to 1 of 2 f squared? You should probably be able to see that answer is just 2 pi squared. Okay, now as far as what I expect, though, I want you to show me the limit rules you used. When you said 2 first, I assume you said, well, that 2 doesn't matter. I need to focus on the limit on the f. So you were, in at least, whether you knew it or not, you were mentally pulling the 2 out front of the limit. And then when you said pi squared, it feels like you then did the limit on f and then squared, which is to say you found that, then squared it. That then is where you get to pi squared. Now in terms of just the big picture, in arithmetic, order of operation is set in stone. You have to add and subtract, after you multiply divide, and those come after you do exponents and roots and all that. That's it. I mean, that matters. You have to do it in the correct order. Higher math, there's some leeway here in terms of integration rules and limit rules. I can do the 2 later. I can do the square later. Limit can come first if it helps me. All right, you with me? All right, that's it. That's pretty much it. If you feel like you can do that, then you can do 69 and 7. Questions? Do you have set 12 still, or did you turn that in? You still have set 12? Okay. Questions on set 12, please. Set 12. All right, anybody else have those info sheets?
Yes.
Stop raising your hand. I hate it when you raise your hand like that. I don't look at your hand. 17. Only the second part. 12. Thank you. Thank you. Answers. All right, 17 and 12. Those are box numbers, I assume?
Yes.
Okay, box 17 and 12. Okay, cool. By the way, as far as how I do this stuff, if you look at 17 and 12 and you didn't have problems with those, then feel free to work on tonight's homework. They're not going to hurt my feelings. If we start talking about something interesting, you should listen to it. I don't care if you don't listen to something you already know how to do. 17. Box 17 is same equation as 16. Second derivative test. Okay, so this is a good question. On the exam next week, I have an exam next week. I think I was going to put it on the bonfire day so you didn't have homework that night, but something like that. We'll see. But this is definitely something I would expect you to be able to do. Can you do the first derivative test first? Can you do the second derivative test first? So, here we go. Is this the correct problem, first of all? Whoever asked this, is this the one you want?
I just want the question at the bottom. Does this equation have absolute?
Oh, gotcha. Does the equation have absolute extrema? Does this violate the extreme value theorem? Okay, gotcha. So, the extreme value theorem actually has 2 pieces. Is if f is continuous on a closed interval, it must have absolute extrema. The second part is those extrema must be are at an endpoint or a critical number, which is not the important part for this problem. Okay, so for this, it helped me to think graphically. Does that have absolute extrema? A max that's greater than y value that's greater than all other y values? No. Does it have an absolute minimum? No. Does that mean the extreme value theorem is garbage and it's all bogus and we've been lied to? No. Why is the extreme value theorem not applicable? Yeah, it's not a closed interval. If they don't close it off, then it's not necessarily applicable in this case. And so I would say something like not applicable because there's no closed interval. That's what I was getting at. Does that make sense? 12. Question on 12. Yes? Is that still a question? Somebody who ever asked 12? Okay, 12. M5. That was in my top packet anymore. M5. All right. Yeah, I didn't do any of these practice. I think this was any work now. I don't think we did any of these practice. You didn't do this one? Oh. All right. M5. M5, okay, got you. I got you. Differentiate y equals arctangent of x over 3. Now, I only did this one day, and I haven't come back to it, so I'm glad you're asking. This is also something I would like to see if you could do on a test. I do not want you to do this by recall. I want you to do it by development, which is to show implicitly why the derivative is what it is, not just throw the derivative at me. If you know the derivative of arctangent of u is 1 over 1 plus u squared, and you use the chain rule, then cool, I'm okay with you knowing that answer to expect. Fine. But as far as actually showing the work, I expect you to show the work. This, just by a check, is fine. Right? So, my expectation is that you would rearrange this so it's an implicit or y implied equation rather than a y explicitly stated equation. Differentiate with respect to x, both sides. The left side derivative is the derivative of the outside, which is secant squared y, times the derivative of the inside, dy dx. Derivative of the right side is strictly just 1/3. dy dx then is the 1/3 is still there. Now I could divide by secant squared, but secant squared in the denominator is the same as cosine squared in the numerator. I think you'll agree. Yeah? All right. The last piece that people tend to forget or get confused by is that the derivative needs to be put in terms of x. So to do that, you go back to the original xy relationship from the problem and think visually. In that statement, y is an angle, x is an opposite side, and 3 is an adjacent side because tangent opposite to adjacent. By Pythagorean theorem, this is the square root of the sum of the legs, root x squared plus 9. If I then use the cosine squared, then the cosine would be adjacent to hypotenuse, or 3 over root x squared plus 9 quantity squared. So all said and done, this is something like 3 over, right, 1, 3 would cancel, over x squared plus 9. With a lot of algebra cleanup, this is. Does that make sense? All right. Any other questions on set 12? Set 13. How did set 13 go? Did it all come back to you or not quite? Okay. Let's talk about a few things. We probably won't get through all of it, so if we turn it in the next day, that's fine. Did one go okay?
Yes.
Is that distance or displacement? It's displacement, unless the function is always positive, in which case it's both. The distance is the displacement, right? All right, so without knowing what the graph looks like, that's displacement, not distance. All right, so let's go to the next guy. This one might have been, I don't know, maybe you got this, maybe you didn't. What were your answers? I know I didn't put the answer in my key intentionally. What did you say? Throw it out. What? E? You guys are smart. Did you just guess well, or you just that smart? Okay, gotcha. So, good. This is a little bit of laying the foundation for an idea to come. So the idea is that you have a city center, and the further you get out from the center, the density gradually changes. And so we want the number of people. Let's start here. Number of people, in terms of the variables and the units, isn't that going to require the density, which is in people per square mile? And then I would have to multiply that by what to get people? Number of square miles. Okay, so use the units as a guide. That's my first hint, all right? Now, the thing, though, is that density is not always the same. It's not like 5 people per square mile times 20 square miles. That's algebra and easy. The density changes. And so how dense it is here is different than how dense it is here. So to do this, I actually need to do lots of calculations. Density here times square miles there. And density here times square miles in that case. And density there and square miles in that case. And then add all those infinitely many, infinitely little calculations. And how do you do that? How do you sum infinitely many, infinitely small? And that's just sum. Okay? All right. So that's how calculus works. Its integration is an infinitely many, infinitely small calculations. So I know the density function. That's cool. That's given. The harder part by far is the how many square miles. Now, normally in Algebra 1, if you wanted to do area of a ring, you would say pi big R squared minus pi little r squared, yeah? The problem, though, is this is a theoretical exercise, kind of, and that is that each of those r's, I mean, it changes all the time. So I can't do a thick ring like that. That's more of a delta r. I need an infinitesimally small r. Not this even is too fat, okay? And so my point is this, those r's, they're not even really different. They're all the same. They're so small difference, they're the same. So that kind of fails, and that is no-go. Instead, think if you took some scissors here, I don't know, is that really worth the time to do that? Okay, but if you took those scissors and cut that and unwrapped it, how would you find the area of that? Let's go here. What's this dimension? That height. Comes from the thickness of this. How thickness is that? How thick is that? What? dr. It is an infinitesimally small change in radius. It's dr. What's this base of the rectangle? Circumference. It's 2 pi r. So if I want the area in a ring, I need to find really the area of a tiny string unwrapped. And so that's 2 pi r dr. The limits of integration. R is the variable of integration. So the limits on R are from what R to what R? 0 to 3. And so the answer is indeed B. 2 pi r, here's the area, this 2 pi r dr represents the area of the little rectangles, and then times the density function gives you P. Okay? That's civil engineering kind of problem. Yay. All right. Anybody interested in civil engineering? At any rate. This guy, I think I intended to change these 10s to something that cube roots nicely. 10 does not cube root nicely, so my bad. The question is, should we change 10 to something nice, or just scratch the no calculator and call it calculator? And, all right, so let's call it yes calculator. All right then. Now that said, I'm going to temper your calculator use, and we're going to use our noggin a little bit. Here's the gallons per minute, and it's going to represent both in and out rates over time. 0 to 81, did you use a scale of, did you go by 9 to 10? 10s make sense. Okay, so 10-minute increments, so good. All right. I'm going to go by ones here, although it tends to get a little off the graph. It works for me. Okay, so check this out. Let's go with the 8 gallon per minute in rate. That's right. This, I missed. This is rate in. What would the area under that curve represent? How many gallons? In at any month. So again, there's all that. The area under the curve, who cares? Well, area under the curve represents gallons in. Gallons per minute times minutes. So it has meaning. What about the other guy? L, lead rate. Well, let's use our noodle again. Just want you to think here. X to the first is straight up linear through a 45-degree angle, right? Now, notice that if you take anything above 1, then it will be above that line or curving above. Anything below that power, x to the 2/3, for example, will be less and curving down. I could pretty well show that this is always concave up. Anything below 1 would be negative concavity, concave down. So I would like you at the least to say, I kind of have a feel for that guy. It's less than x to the first kind of thing. Let's go with at 0. The rate is 0. Good question, Softy. At 1, the rate is 1/2. What's the next good cube root? 8. At 8, we get 2. What's the next good cube root? 27. At 27, we get ish 4.5. Ish. Okay. What's the next good cube root? 8. At 8, or not 8, sorry, 64. At 64, what do we get? 8, yes, at 64, 20, 40, 50, 60, 4, 6, 8. The next good cube root is 125. All right, you with me? All right, now I would like you to, rather than show the rates separately, my goal is that you show a net rate here, a combination rate, in minus out. For obvious reasons, I didn't use O for out, I used L for leave. What's the net rate at time 0? 8. Okay? That net rate would start to decrease, or the difference between them decreases until I get to an x of 64. At that case, they're equal, and so I minus L is 0, and after that, leave is greater, and so the rate is negative. Now, you often will deal with one or the other. Sometimes you're dealing with both separate. Sometimes you're dealing with a net rate graph, a single graph. Either way, you should be able to interpret what's going on in the graph. Over what time frame is the amount of water increasing? From 0 to 64, because in is greater than out. Okay, so it's increasing here, and then after, when out is greater, it is decreasing, yeah? How about here? If the net rate is positive, then the amount of water is increasing. If the net rate is negative, the amount of water is decreasing. Understood? Okay, let's talk these then. How many gallons of water leak out from time 0 to time 10? Do I care about the initial 50 gallons for this question? No. When they ask about leave, all I care is about the leave function. So the leave is constantly changing. It's changing. It's doing different gallons at all these different times. So I have to make lots of little calculations of gallons per minute times little bits of minutes, which is UT. From when to when, 0 to 10. And what are the units on that answer going to be? Don't worry about the number. What are the units? Gallons. Okay. All right. B, how many gallons of water are in the tank? Now, as opposed to the previous question, there are lots of things that go into that. What are the 3 things that go into amount of water in the tank? Initial pressure, how much goes in and how much goes out, right? So how do we structure this? What's the initial amount? 50. That is not going to be integrated. That's just a constant amount. Then I have some accumulation of change, which is to say integration. Do I need to integrate those separately, or can I integrate the net rate? Could I integrate them separately? In integral and out integral separately? Yeah. Could I put them together? Yes. Rules of integrals are, adding and subtracting, you can't separate them, or together they're the same. So if I go with, is the 8 positive or negative? Why is it positive? Because that's water in. Is the 1/2 t cubed positive or negative? Negative, or needs to be subtracted because that's out.
Apologies for the interruption. Just a few updates for 7th hour. There will not be an NJHS meeting today, and Boys Mentoring is meeting in the cafeteria. Thanks, and have a great weekend.
Okay, so 0 to 10, crank that out and call it good. Don't worry about it. I assume you could put that in your calculator. So as long as you have that set up, we're good. What if I wanted, shucks. All right, we'll finish going over on Monday. Have a lovely weekend. Set 12 is due today, but set 13 you can keep. Have a wonderful day. Work on your college essays, you church and seniors. I don't know if you went to college night this week, but the scholarship guy said seniors should be writing or applying for 2 to 3 scholarships.
Just a friendly reminder, there is not an NJHS meeting on Thursday. Again, there is no NJHS
Seriously,
meeting.
he said that.
They are, however,
Do it.
being split their second school.
You're doing it? She is now, baby.
So much pressure.
I don't care. If somebody said, hey, would you write an essay for $500, would you say,
Yeah, but
darn, there you
it's
go.
every week for them. Yeah, I know.
That's your job now.
Sometimes you have to find good colleges that I'll not
Better get on it. All right. Yep.
Also wanted to get a paper one, because I just always forget
Sure.
to check it.
Yeah. Give me a second to dig it up. So you wait to talk to me.
Ian, what is the answer to 19 on
I know,
football?
that's why they put it back. They're trying to get
Wait, I found it.
grades for that.
Yep, got it.
I take it too.
Yes, no, I'm coming. I'm staying there myself. I'm not there. Are you gonna go lunch? Oh my goodness. We were one busy town.
Have a great day. Can I get it to you after a while?
Yes.
Okay, swing by later, or I'll get it to him or something.
Okay. I think I'm gonna be at your house.
Oh yeah, I'll give it to you now. Bye. Alright, so solve for y. So if you're going to solve for y, you have a mixture of y squareds and y's. You usually have to complete the square to do it. So first thing I want you to do is move the y's over to the other side and write that. So on the left side, you're going to have x squared minus 2x minus 4. Now, to solve for y, you want all y's on one side and x on the other. Yeah, no, it's okay. So get the y's on the, make them, I moved them over to the right to make them positive, and the x's can be on the left. Okay. Now the problem with this is to get y by itself, you have to do it all by squares. And so that we would like to get this all to be 1 to the right and 2, so we can get the square. So if you can do the square, what would you add? Add 4, and then for both sides, which is usually 6. So you have x squared minus 2x. On this side, then, this is factored, or we're factoring y plus 2 and y plus 2 and y plus 2 squared. Now you're supposed to get rid of the square y plus 2 plus 1. That would be necessary to put the calculus, to put the graph in function.
Okay, but you can just put numbers.
Exactly, if you didn't want to do that, you could make it. There's some stuff we can do this week, we will follow that one. Okay, roll. Hello.
Oh my god, my pop was up that whole time. Why did you call me 2 times? Oh. People are gonna die. People have to die. Stop how to live.
Okay, Paul,
Here.
Casey,
Here.
Kendall, oh, she had, Colorado, Alex, Ruth, Austin, oh, sorry. Melissa,
Here.
okay, sorry, Brana, Madeline,
Here.
Jaser, Taylor, Wilson, Bryn,
Here.
Robert's even in this meeting. Okay, so I have these people absent: Colorado, Alex, Taylor, and Robert. Okay, boom.
That's the bathroom. He literally just asked me whether he loved it. Oh, no, she was